Okay, so we are back again. So before moving to the next page, that in the previous class I had no calculator. Actually, this is correct. 12.16. So it should be 12.16, not 0.6, right? So this is all your this one 12.16. This is 12.16. So all corrected, right? So therefore, the steady state error you have seen in the previous class lecture that it is VE is a steady state error, it is 0.091. The error is quite high, right? Now, if you plot the dynamic responses, right, Vt versus time, it is 20-second time. Although I have shown few oscillations may be very the oscillations may be more, right? It may be like this, it may be like this, maybe like this. I mean, it may be like this, right? So if you plot using your what you call that your Simulink or any other packages, this is the time, it is given up to 20 seconds, and this is your it is given step input, that is 1 per unit voltage 1 upon S. So ultimately it is settling to your it is going like this and settling to your 1.0, but peak deviation is quite high, right? Whatever parameters we have taken, and your terminal voltage, this is terminal voltage step response, right? V reference is equal to, we have taken 1 upon S, right? So next is excitation system stabilizer rate feedback. Here one correction you have to make it, that this is actually just hold on. So this is actually your SKF, right? Just hold on. So this is actually SKF, the derivative feedback. So this is when I am making it, it was actually I missed this S, so it should be corrected. So this is actually one stabilizing transformer is there, right? And it is excited by your this voltage Vf, right? Exciter voltage. And if you find out this transfer function, it will be in this form SKF upon 1 plus STF. I suggest look any book, you will get this your what you call this transfer function of stabilizing transformer, and I have given. So it is actually it is SKF upon 1 plus STF. So previously this feedback was there, but one inner loop it is there and it going here. Right? Different. It has some your what you call some other version of representing this one, but I have taken this one. So this is actually your what you call that block diagram of the compensated AVR system. This actually improves the dynamic performances because this is a rate feedback. This is actually when I am cleaning it, it is SKF upon 1 plus STF. So in the previous example, we have seen that for small amplifier gain of K is equal to 10, AVR step response is not satisfactory, and a value exceeding 12.16, it is 12.16, right, results in an unbounded response. So that means unstable. Thus, we must increase the relative stability by introducing a controller which would add a 0, right? Which would your just hold on. So which would add a 0 to the AVR, open loop transfer function. So one way to do this is to add a rate feedback to the control system as shown in figure 3. So this is actually your rate feedback. I told you this is a correction, it should be SKF upon 1 plus STF, and this is a stabilizing transformer, we call it stabilizer. So its transfer function will be like this. Just I suggest that you see any book, it is a small 4-5 lines derivation, but I am not putting it here, right. So we should add a 0 to the AVR. One way, so figure by proper adjustment of KF and TF, a satisfactory response can be obtained. For example, suppose Kf is equal to 2.0 and Tf is equal to 0.04 second. All the parameters remain as in the previous example. So, whatever parameters we consider, that was your what you call same, only Kf is equal to 2 and Tf is equal to 0.04 second we have assumed. So, obtain the steady state response, we have to obtain the steady state response. That is, the response means the steady state value, say VTSS, right. So, when you find out the closed loop transfer function of that system, that is in figure 3, right, you will find Vt upon V reference is equal to 250 into S square plus 45 S plus 500 divided by S to the power 5 plus 58.5 S to the power 4 plus 13,645 S cube plus 20 your what 2,70,962.5 S square plus your 2,74,875 S plus 1,37,500. So, this will be your what you call the transfer function after substituting all the values, right. Therefore, now first one is the steady state response is, if you put limit actually V reference is equal to 1 upon S. If you put V reference will be 1 upon S. So, this side actually automatically will become S VTS and then you are taking limit S tends to 0. So, if you make S tends to 0, right, then this one will be 0, this one will be 0. So, 250 into 500 the numerator and denominator will be all will be 0, these are all zeros. So, only 137,500, 137,500. So, its value is coming 0.909, right. So, this is actually steady state value of VTSS. Now, if you plot that terminal voltage Vt, right. So, it is up to 10 second and this is Vt is equal to 1.0. So, you will find that there is no overshoot here, but it is settling to some value, say nearly 0.9, we have saw we have seen that it is 0.909. So, it is 1.0, but still not achieving to 1.0, but it is showing 0.909. So, this is terminal voltage step response, right. So, this is actually I think it will be figure 4, not figure 3, previous one was figure 3, right. So, next is that your excitation system stabilizer, that is PID controller. Now, if you use that one PID controller Kp plus Ki upon S and plus SKD, and this is your as usual amplifier, exciter, generator, and this is VTS. No stabilizer is here, that is no stabilizing transformer is connected here, right, and this is a PID controller. So, optimization nothing will be discussed here, just we will see how the response is for a particular value of Kp, Ki and Kd, right. So, this will be then your figure 5, then not 4, just check it, correct it. So, figure number is not a problem, our thing is that look into that. So, suppose Kp is equal to 1, proportional gain is 1 for that PID controller, Ki is equal to 0.25 and Kd is equal to 0.28. This you have taken, we have taken. If you see this, then you will find that your just hold on. Then you will see that Vt that is your 1.0. So, with that with PID controller it is actually settling to 1.0. So, and it is actually at settling nearly 2.0 second, right, and this is terminal voltage step response. No figure number for this one, but there is no overshoot here, right. There is, because of derivative action, oscillations have been wiped out and there is no your what you call that overshoot, there is no overshoot, and it settling here somewhere nearly 2 seconds. So, when you are putting PID controller, you can see that your settling time is very less, right. So, with this your reactive power voltage control is this much, but if I don't think time will permit. If permits, I will see that how AGC system and excitation system and PF and QB loop how to couple it, right. Although coupling effect is negligible, but how to couple it, if time permits I will make it for you, right. So, with this Next one is that your state estimation. Just hold on. Next one is that your state estimation. So, in this case, so what is state estimation and state estimation in power system? Actually, what happened, just if we start with this, that when you are suppose when you are doing in experiments in the laboratory, you have so many meters like voltmeter, ammeter, wattmeters and other types of meters. So, when you are taking the reading using all these instruments, you will find that there must be some error, because you cannot take the exact reading, right. Suppose when you are connecting, when you are trying to take readings of wattmeter, voltmeter or ammeter, you will find the pointer actually oscillating around some point, that is around the your what you call that your exact reading, but ultimately whatever reading you take, that is it is not a correct one, because measurement error is there. This is one thing. And another thing is, if you I am not sure that your anything is written or not, and the your what you call instrument, the accuracy, sometimes it may be given the accuracy is plus minus 3% or plus minus 1%, right. So, that is actually accuracy means it is a 3 sigma, that is if you have a normal distribution, it is a 3 sigma, that is basically a standard deviation, right. So, whenever you are measuring certain quantities, that it has some error, right. It is not correct one, it is not the your exact one, right. So, sometimes measured value we will call it as a true value, and there are many state variables are there, and you are taking measurements, right, but those measurements have error, right. So, we have to find out some methodology such that we can estimate those parameters, it is as close as the true value by even correct value, right. That is the idea. So, that means a state estimation, it is the process of assigning a value to an unknown system state variable, right, based on measurements from that system according to some criteria, right. We will see what is that criteria. So, that means idea is that assigning a value to an unknown system state variable based on measurement from the system according to some criteria. That means, you are measuring the value, but those measured value have error, right. It is not a correct one, but using those data, that measured data, we will try to estimate this value, which will be as close as the correct value, right. So, this is the idea for state estimation. Actually, state estimation concept first developed for aerospace engineering, right. In after that, in at the end of your 1960s, right. So, application came to the power system, and after that people have found that this technique is very useful, the state estimation concept is very useful, right. So, you may have suppose you may have your what you call sometimes, suppose you have number of state variables are known to you, how many state variables you have to estimate. Sometimes number of measurements are more than number of state variables, sometimes number of measurement less than number of state variables, and sometimes number of measurement is equal to number of state variables. So, because of this, you have a different type of concept and different type of mathematical derivation, right. So, usually the process involves an imperfect measurement that is redundant, and the process of estimating the system states is based on a statistical criterion, right, that actually estimate the true value of the state variables. True means in this case we will call it as a measured value, right, to minimize or maximize the selected criterion, right. So, a commonly used and familiar criteria is that of minimizing the sum of the squares of the differences between the estimated and true, that is measured values of a function, right. We will see that. So, this is actually your what you call that true value means we will define it, that is a measured value. So, in many applications measurements may be contaminated with noise and may contain system measurement errors, because it may not be correct one, measured value may not be correct one, it has some errors. And if you have your if it is a large system, suppose if you have a large system say 100 bus problem, and if you are measuring that all the bus voltage magnitude, right. Even each bus voltage magnitude, some error will be there, small error will be there, but if you see 100 buses are there, then gross error will be high, right. But we have to estimate using those measurement data, we have to estimate those bus voltage which will be as close as the correct value, right. That is the idea for state estimation. And generally state estimation have two types, static and dynamic. So, in this course we will study the static state estimation, but not much in detail, right. So many things are there which cannot be solved in the class, particularly for AC state estimation it is impossible to solve in the classroom, you need computer, but we have to see things that we can solve in the classroom, right. So, state estimation may be both static and dynamic, right. So, both type of estimators have been developed for power system. In a power system, the state variables are the voltage magnitudes and phase angles, right. At the node, actually here that during scanning, that E has cut, actually it is node, right, or bus. So, basically it is not only the voltage magnitude and phase angles, but also the power, the megawatt, real power, the reactive power megavar, or that MVA, that is your megavolt ampere, or the transformer tap changes setting, right. So, all these things are there. So, but here will that we will see when we will consider the AC state estimation for AC network, right. So, voltage magnitude or phase angle at the node or buses, right. So, measurements are required in order to estimate the system performance in real time for both system security control and constraint on economic load dispatch, right. So, inputs to an estimator are imperfect power system measurement, because when you are putting this your what you call input to the estimator. So, basically it is measurements are not correct, we are assuming that measurements are not correct, and voltage magnitude and power, that is or volt ampere or ampere flow quantities, right. So, the estimator is designed to produce the best estimate of the system voltage and phase angles, say, right. So, recognizing that there are errors in the measure quantity. So, we are assuming that whatever you are measuring through the instrument, it has the error, right, and that there may be redundant measurements also. So, suppose you have, for example, suppose you have 3 state variables, but your number of measurement data are more, but we have to see that how to utilize that one, that we will see. So, power system state estimation. So, the problem of monitoring the power flows and voltages on a transmission system is very important in maintaining system security, right. By simply checking each measured value against its limit, the power system operators can tell where problem exists, right, in the transmission system, and it is hoped that they can take corrective action to relieve overloaded lines or out of limit voltages, right. So, what you call the problem of monitoring the power what you call power flows and voltages on a transmission system is very important in maintaining system security. So, power system operators, when they will see the overloaded line or the bus voltage are also crossed its limit. So, they can take the looking at that they can take the corrective action, right. So, many problems are encountered in monitoring a transmission system. These problems came primarily from the nature of the measurement transducers and from communication problems, right. In transmitting the measured values back to the operation control center. So, transducer from power system measurements, like any measurement device, will be subject to errors. So, nothing is error free, you will have error, right. So, if the errors are small, they may go undetected and can cause misinterpretation by those reading the measured values, right. So, even if the errors are small, they may go undetected and can cause misinterpretation by the reading of the measured values. So, in addition, the transducers may have gross measurement errors that render their output useless, right. So, the telemetry equipment often experiences periods when communications channels are completely out. This is another problem, right. Thus, depriving the system operator of any information about some part of the power system networks. That means, that is actually this due to the communication channel failures, right. So, because data has to be transmitted to the control center. So, it is for these reasons that power system state estimation techniques have been developed, right. So, a state estimator can smooth out small random errors in meter readings, detect and identify gross measurement errors, and fill in meter readings that have failed due to communication failures. So, this is the important thing for your what you call state estimation in electrical engineering, particularly in power system, right. So, before that, actually when you will go for state estimation mathematical thing, that we will start with DC load flow method, right, DC load flow. That is why I thought before moving further, let us little bit discuss about the what is DC load flow, right. So, the DC load flow simplifies the AC load flow to a linear circuit problem. Those who have gone through that your little bit on DC load flow, they know it, but here I will make it in brief, not in detail, very simple thing. Consequently, it makes the steady state analysis of the power system very efficient, quickly you will get the result, although result may not be exact, but it helps a lot, right. The main shortcoming of the DC load flow model is that it cannot be used in checking voltage limit violations, right. So, voltage limit violations you cannot check it, because the DC load flow uses a linear model. It is not only suitable to efficiently treat the problem of your line outages, but is also suitable to from linear optimization problem. So, it is directly you will get the solution, right. So, no question, no iterative method, whatever little bit we will study. Therefore, the DC load flow method has been widely used in power system planning and operating problems. So, here also for state estimation we will see first DC load flow. Now, model of DC load flow. The node active power equations of an AC load flow are given by, right. So, different book has different convention. So, here I have taken some convention. Actually, whatever convention is there, you can take it, no problem, right. So, that power injection P I is equal to, you know that V I, then J belongs to I. So, V J G I J cos theta I J plus B I J sin theta I J. It depends, this sign before B I J, it depends on B is negative and positive, that is whatever way you study does not matter, final result will remain same. For I is equal to 1 to n, this is equation I put 0 1, right. So, later we will make 1 2 3, but separate note has been made. So, it is 0 1. So, branch active power is, that is the power flows from branch I to J, it is V I V J, then in bracket G I J cosine theta I J plus B I J sin theta I J minus T I J G I J V I square, right, where T I J the circuit transformer ratio per unit branch I J, right, per unit of branch I J. So, this is that circuit transformer ratio sorry, and theta I J the phase angle difference across branch I J, this is your theta I J, and G I J B I J both the real and imaginary parts of corresponding elements of the node admittance matrix respectively. This you know, conductance and susceptance, right. So, and theta I J we know that theta I minus theta j, this is equation 03, right. Now, we will define something that G I J plus J B I J is equal to minus of 1 upon R I J plus J X I J. Just we have defined, generally it is, I told you this sign actually depends the way you take. So, we have to, if you take minus, then minus 1 upon R I J plus J X I J. So, this part will be minus R I J upon R I J square plus X I J square plus J X I J divided by R I J square plus X I J square. This I have taken, later we will see that we will simply take that your G I J plus J B I J, right, is equal to, actually it is 1 upon R I J plus J X I J, that is nothing but your R I J divided by R I J square plus X I J square, then minus J X I J divided by R I J square plus X I J square, right. But here we have taken a minus for the convention, the way I think different book might have taken different thing, right. So, it does not matter, later we will see that we will use this convention only, right, your what you call for your Bij. So, in that case, suppose for this case, suppose if you just neglect r, because for transfer for just for the your what you call simplicity, suppose if we neglect r, because transmission line the r is very small compared to x. So, let us neglect r. So, if you neglect r, then the g should not be there. If you neglect r, g should not be there, right. So, in that case your what you call, we write like this, that your Gij, right, plus j Bij is equal to, say, if you write like this, minus 1 upon, forget about minus 1 upon Rj plus j Xij, right. If you write like this and keep it minus, it does not matter, keep it minus 1 upon Rij plus j Xij. Now, as r is neglected, so r should not be there here. So, g also should not be there because g is equal to this much and r is equal to 0, say it is neglected. Therefore, what we will see that j Bij is equal to, actually it will become 1 upon minus 1 upon j Xij, right. Now, if you cross multiply, then I am overwriting on it, right, then it will be j square Bij, right, is equal to minus 1 upon Xij, right. That means j square is minus. So, minus minus will be cancelled both side, therefore, your Bij is equal to 1 upon Xij, right. So, we are later we will see that for DC load flow r will be neglected. So, with this, that your, so where Rij, Xij, resistance and reactance of the line Ij or branch Ij respectively, when I is equal to j, Gi will be is equal to sigma minus your sigma j belongs to I, but j not is equal to I, that is Gij, right. So, a minus sign will be there before that. Thank you very much, we will be back again.